हेलो फ्रेंड्स, आज हम लोग क्लास 11 केमिस्ट्री चैप्टर 10 जो एस ब्लॉक एलिमेंट है उसे पढ़ेंगे। तो उसे बेसिकली हम द फर्स्ट एलिमेंट ऑफ अल्कली एंड अल्कलाइन अर्थ मेटल डिफर इन मैनी रेस्पेक्ट्स फ्रॉम द अदर मेंबर्स ऑफ द ग्रुप. The s block elements of the periodic table are those in which the last electron enter the outermost s orbital. As the s orbital can accommodate only two electrons, two groups 1 and 2 belongs to s block of periodic table. Group 1 of the periodic table consists of elements lithium, sodium, potassium, rubidium, cesium and francium. They are collectively called the alkaline earth metal. These are so called because they form hydroxide on reaction with water, which is strongly alkaline in nature. The elements of group 2 include beryllium, magnesium, calcium, strontium, barium and radium. These elements, with the exception of beryllium, are commonly known as alkaline earth metal. These are so called because their oxides and hydroxides are alkaline, means basic, in nature, and these metal oxides are found in earth crust. Among all the alkali metals, sodium and potassium are abundant, and lithium, rubidium and cesium have much lower abundance. Francium is highly radioactive. Its longest lived isotope, francium 223, has a half-life of only 21 minutes. Of the alkaline earth metals, calcium and magnesium rank 5th and 6th in abundance respectively in earth crust. So this is important part, underline this part till crust. And strontium and barium have much lower abundance. Beryllium is rare and radium is rarest of all, comprising only 10 to the power minus 10% of igneous rocks. The general electronic configuration of s block elements in noble gas NS1. This is the electronic configuration given for alkali metals, and noble gas NS2 for alkaline earth metals. Now, lithium and beryllium, the first elements of group 1 and group 2 respectively, exhibit some properties which are different from those of other members of respective group. In these anomalous properties, they resemble the second element of the following group. Thus, lithium shows similarity to magnesium and beryllium to aluminium in many of their properties. This type of diagonal similarity is commonly referred to as diagonal relationship in the periodic table. The diagonal relationship is due to similarity in ionic sizes and or charge and radius ratio of elements. Monovalent sodium and potassium ions and divalent magnesium and calcium ions are found in large proportions in biological fluids. These ions perform important biological functions such as maintenance of ion balance and nerve impulse conduction. Now coming to group 1 elements, which are also called alkali metals. The alkali metals show regular trend in their physical and chemical properties with the increasing atomic number. The atomic, physical and chemical properties of alkali metals are discussed below. The first property is electronic configuration. All the alkali metals have one valence electron, Ns1. Outside the noble gas core, the loosely held s electrons in the outermost valence shell of these elements makes them most electropositive elements. They readily lose electron to give monovalent M+ ions. Hence, they are never found in free state in nature. It means they are very reactive and always react with other compound and never found in free state. Now, this is a table which you can see. The configuration of lithium, sodium, potassium, rubidium, cesium and francium are given. And now, coming to atomic and ionic radii, the alkali metal atoms have the largest sizes in the particular period of periodic table. With increase in atomic number, the atoms becomes larger. So as we increase the atomic number, the size of alkali metals becomes larger. The monovalent ions M+ are smaller than the parent atom. The atomic and ionic radii of alkali metals increase on moving down the group. They increase in size while going from lithium to cesium. Now coming to ionization enthalpy. The ionization enthalpies of alkali metals are considerably low and decrease down the group from lithium to cesium. This is because the effect of increasing size outweighs the increasing nuclear charge, and the outermost electron is very well screened from nuclear charge. Now, one question must be come to your mind: what is ionization enthalpy? So ionization enthalpy is the energy required to remove the electron from the outermost shell. So this is now coming to hydration enthalpy. The hydration enthalpy of alkali metals ions decrease from increase in ionic sizes. Lithium has maximum degree of hydration, for a reason lithium salts are mostly hydrated. Now coming to physical properties. All the alkali metals are silvery white, soft and light metals. Because of larger size, these elements have low density which increases down the group from lithium to cesium. However, potassium is lighter than sodium. The melting and boiling point of alkali metals are low, indicating weak metallic bonding due to presence of only a single valence electron in them. The alkali metals are their salt impart characteristic color to an oxidizing flame. This is because the heat from flame excites the outermost orbital electron to the higher energy level, which then excited electron comes back to the ground state. There is emission of radiation in the visible region as given below. Lithium, while we burn lithium, the color of the flame is crimson red. In sodium it's yellow, in potassium it's violet, in rubidium it's red violet, and in cesium it's blue. Alkali metals can therefore be detected by the respective flame tests and can be determined by flame photometry or atomic absorption spectroscopy. These elements, when irradiated with light, the light energy absorbed may be sufficient to make an atom lose electron. This property makes cesium and potassium useful as electrode in photoelectric cells. Chemical properties. The alkali metals are highly reactive due to their large size and low ionization enthalpy. It means their size is very large and hence their ionization enthalpy is very large, which means it is very easy to pull out the outermost electron as there is very less influence of positive charge of nucleus due to large size. The reactivity of these metals increases down the group. Reactivity towards air. The alkali metals tarnish in dry air due to formation of their oxide, which in turn react with moisture to form hydroxide. They burn vigorously in oxygen, forming oxide. Lithium forms monoxide, sodium forms peroxide, and the other metals form superoxide. Now what is superoxide? The superoxide O2- ion is stable only in the presence of large cations such as rubidium, cesium, potassium, rubidium and cesium. Now there is a reaction given, for example, for lithium, if we will take 4 atoms of lithium and it combines with 1 O2, then it produces 2 lithium 2 oxide. It means dilithium oxide. It is lithium oxide. Now reactivity towards water. The alkali metals react with water to form hydroxide and dihydrogen. Now 2M means 2 magnesium reacts with 2 moles of water to form 2 positive ions of or 2 ions of magnesium with 2 OH- ions plus release of hydrogen gas. It means that when we will put magnesium in the water, it will release hydrogen gas. This hydrogen gas is released from the test tube. It may be noted that although lithium has most negative value, its reaction with water is less vigorous than that of sodium, which has least negative value among the alkali metals. This behavior of lithium is attributed to its small size and very high hydration energy. Other metals of group react explosively with water. They also react with proton donors such as alcohol, gaseous ammonia and alkyne. Now reactivity towards dihydrogen. Now dihydrogen is simply H2. The alkali metals react with dihydrogen at about 673 Kelvin to form hydrides. All the alkali metals, hydrides and ionic solids with high melting point, 2 moles of magnesium plus 1 mole of dihydrogen forms 2 positive ions of magnesium and negative ions of hydrogen. Now what is the reactivity towards halogens of alkali metals? The alkali metals readily react vigorously with halogen to form ionic halides M plus X minus. However, lithium halides are somewhat covalent. It is because the high polarization capability of lithium ion. The lithium plus ion is very small in size and has high tendency to distort electron cloud around the negative halide ion. Since an ion with large size can be easily distorted. Among halides, lithium iodide is most covalent in nature. Now reducing nature. Reducing nature. The alkali metals are a strong reducing agent. Lithium being the most and sodium the least powerful. The standard electrode potential, which measures the reducing power, represent the overall charge, M solid to M gas. Now, turning into gas from solid is called sublimation enthalpy. Now, turning into ion or simply removing one electron, the energy required to remove one electron is called ionization enthalpy. And then, what is hydration enthalpy? When we put M plus, which is in gaseous form, in water, it will form M plus aqueous. The energy required in this is called hydration enthalpy. With the small size of ion, lithium has the highest hydration enthalpy, which accounts for its high negative value and its high reducing power. Now there is a problem given. The electrode potential for Cl2 or Cl minus is plus 1.36 and I2 or I minus is plus 0.53. For Ag plus or Ag, it's plus 0.79 and Na plus Na is minus 2.71, and for lithium plus lithium is 3.04. Arrange the following ionic species in decreasing order and reducing strength. Now the solution is given. The order is lithium greater than sodium, greater than iodine, negative ion of iodine, greater than Ag or silver, greater than Cl minus. Now, solution in liquid ammonia. The alkali metal dissolve in liquid ammonia, giving deep blue solution which are conducting in nature. Now here is the reaction given. M plus X plus Y NH3 forms M NH3 X plus E NH3Y. The blue color of solution is due to ammoniated electron which absorbs energy in visible region of light, thus imparts blue color to the solution. The solution are paramagnetic and on standing slowly liberate hydrogen, resulting in formation of amide. So amide is formed here. In concentrated solution, the blue color changes to bronze color and becomes diamagnetic. Now uses. What are the uses of alkali metals? What are the uses of alkali metals? Lithium metal is used to make useful alloys. For example, with lead to make white metal bearing for motor engine, with aluminium to make aircraft parts, and a magnesium to make armor plates. It is used in thermonuclear reactions. Lithium is used to make electrochemical cell. Sodium is used to make sodium or Pb alloy. Pb means lead alloy needed to make PbEt4. Et is simply ethyl, and PbMe4. Me is methyl. These organolate compounds were earlier used as anti-knock additives to petrol, but nowadays vehicles use lead-free petrol as lead is very harmful. Liquid sodium metal is used as coolant in fast breeder nuclear reactors. Potassium has a vital role in biological system. Potassium chloride is used as a fertilizer. Potassium hydroxide is used in the manufacture of soft soap. It is also used as an excellent absorbent of carbon dioxide. Cesium is used in devising photoelectric cells. Now, general characteristics of compounds of the alkali metals. All the common compounds of alkali metals are generally ionic in nature. Generally, characteristic of some of their compounds are discussed here. Now, first, oxides and hydroxides. Now, what are the properties of oxides and hydroxides of alkali metals? On combustion in excess of air, lithium forms mainly the oxide Li2O plus some peroxide like Li2O2. Sodium forms peroxide Na2O2 and some superoxides NaO2, whilst potassium, rubidium and cesium forms superoxide MO2. Under appropriate conditions, pure compound M2O and M2O2 and MO2 may be prepared. The increasing stability of peroxide or superoxide as the size of metal or ion increases is due to stabilization of large anions by larger cations through lattice energy effect. These oxides are easily hydrolyzed by water to form hydroxides according to following reaction. M2O means plus M2O, this is oxide of the alkali metal when added to water forms 2M plus 2 OH minus. So it makes the solution basic. As you can see, the OH minus concentration increases in water. As you can see, there is not only OH ion in the M2O, but it dissociates the H2O into OH minus and it becomes basics. And M2O2 plus 2H2O forms 2M plus 2 OH minus plus H2O2. 2MO2 plus 2H2O forms 2M plus 2 OH minus plus H2O2 plus O2. The oxides and peroxides are colorless when pure, but the superoxides are yellow. The color is given, this is very important. The oxides and peroxides are colorless when pure. The oxides and peroxides of the alkali metals are colorless when they are pure, but superoxides are yellow or orange in color. The superoxides are also paramagnetic. Now, what is paramagnetic? If you have in case forgot, it has half partially filled orbitals, so it is paramagnetic. And what does paramagnetic means? Means it is affected by magnet. Paramagnetic means it is attracted towards magnet, not so as iron but somewhat. Sodium peroxide is widely used as an oxidizing agent in inorganic chemistry. Now here is a problem given, you can see that. Now the hydroxide which are obtained by reaction of oxides with water are all white crystalline solids. The alkali metals hydroxide are strongest of all bases and dissolve freely in water with evolution of much heat on account of intense hydration. Now coming to halides of alkali metals. The alkali metals halides MX like XF or XCl or XBr or XI are all high melting, means they have very high melting points. Very high melting points means what? They are very much stable. They are colorless crystalline solids, like you can see a live example like NaCl. It's also a halide of alkali metal sodium, and you can see it's a crystalline solid and it's also colorless. They can be prepared by the reaction of appropriate oxide, hydroxide or carbonate with aqueous hydrohalic acid. All these halides have high negative enthalpies of formation. The delta of formation means heat of formation of H minus. Values of fluoride becomes less negative as we go down the group, while the reverse is true for delta of formation means heat of formation H minus for chlorides, bromides or iodides. For a given metal, heat of formation H minus always become less negative from fluoride to iodide. The melting and boiling points always follow the trend fluoride greater than chloride greater than bromide greater than iodide. All these halides are soluble in water. The low solubility of lithium fluoride in water is due to its high lattice enthalpy, where the low solubility of cesium iodide is due to smaller hydration enthalpies of its two ions. Other halides of lithium are soluble in ethanol, acetone and ethyl acetate. Lithium chloride is soluble in pyridine also. Now coming to salt of oxoacids. Oxoacids are those in which the acidic proton is on a hydroxyl group with an oxo group attached to the same atom. Carbonic acid, sulfuric acid and the alkali metals form salt with the oxoacids. These are generally soluble in water and thermally stable. They are carbonates, and in most cases the hydrogen carbonates are also highly stable to heat. As the electropositive character increases down the group, the stability of carbonates and hydrogen carbonates increases. Lithium carbonates is not so stable to heat. Lithium carbonate, being very small in size, polarizes a large CO3 2- ion, leading to formation of more stable Li2O and CO2. Its hydrogen carbonate does not exist as a solid. Now there is some anomalous properties of lithium. Anomalous means different properties. The anomalous behavior of lithium is due to the exceptionally small size and its atom and ion. Means what does it means? Anomalous property means there is a trend in the S block elements in the alkali metals in the S block elements, but lithium shows some differences. Now why this difference comes? Now the first reason is exceptionally small size of atom, means the size of atom of lithium is very small, and ions. Second, high polarizing power, which is charge by radius ratio, means the charge by radius ratio, which you can understand easily. As a result, there is increased covalent character of lithium compound, which is responsible for their solubility in organic solvent. Further, lithium shows diagonal relationship to magnesium. It means its property somewhat matches to magnesium, which has been discussed subsequently. Points of difference between lithium and other alkali metals. Lithium is much harder. Its melting point and boiling point are higher than the other alkali metals. Lithium is least reactive but a strongest reducing agent among the alkali metals. On combustion in air, it forms mainly monoxide like lithium 2O and nitride lithium 3N. Unlike other alkali metals, means lithium is least reactive but the strongest reducing agent among all the alkali metals. On combustion in air, it forms mainly monoxides like lithium 2O and nitride lithium 3N. Unlike other alkali metals, means other alkali metals show somewhat different behavior from this. Now lithium chloride is deliquescent and crystallizes as a hydrate, lithium chloride .2H2O, whereas other alkali metal chloride do not form hydrates. Lithium hydrogen carbonate is not obtained in the solid form, while all other elements form solid hydrogen carbonate. Lithium, unlike other alkali metals, form no ethanide on reaction with ethyne. Lithium nitrate, when heated, gives lithium oxide Li2O, whereas other alkali metals nitrates decompose to give the corresponding nitrite. 4LiNO3 gives 2Li2O plus 4NO2 plus O2. 2NaNO3 gives 2NaNO2 plus O2. And lithium fluoride and lithium 2 oxide are comparatively much less soluble in water than the corresponding compound of other alkali metals. Now, what are the points of similarities between lithium and magnesium? Or we are explaining much better the diagonal relationship. The similarity between lithium and magnesium is particularly striking and arises because of their similar sizes. Now, which means that there is some similarity in the size of lithium and magnesium. The similarity between lithium and magnesium is particularly striking and arises because of their similar sizes. Atomic radii of lithium is 152 picometer and magnesium is 160 picometer. So you can see this it's very close. Now, talking about ionic radii, lithium positive has 76 picometer and magnesium 2 positive is 72 picometer. It's more closer, like only 4 picometer difference. Now 1 picometer is very much small. Like the main points of similarity are, now what are the main points of similarity? Let's see. First is both lithium and magnesium are harder and lighter than other elements in the respective groups. Lithium and magnesium react slowly with water. Their oxides and hydroxides are much less soluble and their hydroxide decompose on heating. Both form a nitride Li3N and Mg3N2 by direct combination with nitrogen. The oxides Li2O and MgO do not combine with excess oxygen to give any superoxide. The carbonates of lithium and magnesium decompose easily on heating to form the oxide and CO2. Solid hydrogen carbonates are not formed by lithium and magnesium. Both lithium chloride and magnesium chloride are soluble in ethanol. Both lithium chloride and magnesium chloride are deliquescent and crystallize from aqueous solution as hydrate. Lithium chloride .2H2O and magnesium chloride .8H2O. Now, coming to some important compounds of sodium. Industrially important compounds of sodium include sodium carbonate, sodium hydroxide, sodium chloride and sodium bicarbonate. The large-scale production of these compounds and their uses are described below. Sodium carbonate, which is basically washing soda, its formula is Na2CO3.10H2O. Sodium carbonate is generally prepared by Solvay process. In this process, advantage is taken of low solubility of sodium hydrogen carbonate, whereby it gets precipitated in reaction of sodium chloride with ammonium hydrogen carbonate. The latter is prepared by passing CO2 to the concentrated solution of sodium chloride saturated with ammonia, where ammonium carbonate followed by ammonium hydrogen carbonates are formed. The equations for complete process may be written as now 2NH3 plus H2O plus CO2 gives NH4 twice CO3. Now NH4 twice CO3 when added with water and CO2 gives 2NH4HCO3, and then this NH4HCO3 when reacts with NaCl or sodium chloride forms NH4Cl plus NaHCO3. Sodium hydrogen carbonates crystal separates. These are heated to give sodium carbonates. Now 2NaHCO3 gives Na2CO3 plus CO2 plus H2O. In this process, NH3 is recovered when the solution containing NH4Cl is treated with CaOH twice. Calcium chloride is obtained as a byproduct. Now 2NH4Cl plus CaOH twice gives 2NH3 plus CaCl2 plus H2O. It may be mentioned here that Solvay process cannot be extended to the manufacture of potassium carbonate because potassium hydrogen carbonate is too soluble to be precipitated by addition of ammonium hydrogen carbonate to a saturated solution of potassium chloride. Now coming to the properties, sodium carbonate is a white crystalline solid which exists as a decahydrate, which means 10 molecules of crystallization. Now Na2CO3.10H2O. This is called washing soda. It is readily soluble in water. On heating, the decahydrate loses its water of crystallization to form monohydrate. Above 373 Kelvin, the monohydrate becomes completely anhydrous and changes to white powder called soda ash. Now Na2CO3.10H2O at 375 Kelvin forms Na2CO3.1H2O plus 9H2O. Now Na2CO3 when temperature is greater than 373 Kelvin forms Na2CO3 and that 1H2O is also removed, which means anhydrous Na2CO3 is formed. Now carbonate part of sodium carbonate gets hydrolyzed by water to form an alkaline solution. CO3 2- when added to water, it forms HCO3- plus OH-. What are the uses? It is used in water softening. Means if a question comes in exam, name a compound which is used for softening the water, you can answer this. Na2CO3. And laundering and cleaning, it is used for cleaning purpose, and the detergent we used for your information is also this Na2CO3.10H2O. It is used in manufacture of glasses, soap, borax and caustic soda. It is used in paper, paints and textile industries. It is important laboratory reagent both in qualitative and quantitative analysis. Sodium chloride NaCl. The most abundant source of sodium chloride is seawater. Now seawater is the most abundant source of sodium chloride, which means very much sodium chloride is extracted from seawater, which contains 2.7 to 2.9% by mass of salt. In tropical countries like India, common salt is generally obtained by evaporation of seawater. Approximately 50 lakh tons of salt are produced annually in India by solar evaporation. Crude sodium chloride, generally obtained by crystallization of brine solution, contains sodium sulfate, calcium chloride and magnesium chloride as impurities. Calcium chloride CaCl2 and magnesium chloride MgCl2 are impurities because they are deliquescent, which means absorb moisture easily from the atmosphere. To obtain pure sodium chloride and crude salt is dissolved in minimum amount of water and filtered to remove insoluble impurities. The solution is then saturated with hydrogen chloride gas. Crystals of pure sodium chloride separate out. Calcium and magnesium chloride, being more soluble than sodium chloride, remains in solution. Now sodium chloride melts at 1081 Kelvin. So you can see this is a very high temperature. It has solubility of 36 gram in 100 gram of water. Means at 273 Kelvin we can dissolve 36 gram of sodium chloride if we will take 100 gram of water. The solubility does not increase appreciably with increase in temperature, which means by increase in temperature very less solubility is increased. It is not appreciable or comparable. Now what are the uses of sodium chloride? It is used as common salt or table salt for domestic purpose. It is used for preparation of Na2O2 and NaOH and Na2CO3. Now coming to the next compound, which is sodium hydroxide or caustic soda. NaOH. Sodium hydroxide is generally prepared commercially by electrolysis of sodium chloride in Kastner-Kellner cell. A brine solution is electrolyzed using the mercury cathode and carbon anode. Sodium metal discharged at the cathode combines with mercury to form sodium amalgam. Sodium amalgam is the compound of mercury. Chlorine gas evolved at anode. Now see at cathode what happens. This Na plus gets one electron, and in the presence of Hg, which is mercury, it forms sodium amalgam. Now at anode, Cl minus loses its electron and forms half Cl2 plus one electron is lost. Now half Cl2 means if we will take 2 Cl minus, then it will form Cl2. The amalgam is treated with water to give sodium hydroxide and hydrogen gas. Now 2Na amalgam plus 2H2O forms 2NaOH plus 2Hg plus H2. Sodium hydroxide is a white translucent solid. Translucent means we can not see. It means you know transparent means it is not transparent. It melts at 591 Kelvin. It is readily soluble in water. To give a strong alkaline solution, crystal of sodium hydroxide are deliquescent. The sodium hydroxide solution at the surface reacts with CO2 in the atmosphere to form Na2CO3. Now what are the uses? It is used in manufacture of soap, paper, artificial silk and number of chemicals. In petroleum refining, in the purification of bauxite, in the textile industries, for mercurizing cotton fabrics, for the preparation of pure fats and oils as a laboratory reagent. Sodium hydrogen carbonate, baking soda, NaHCO3. Now we will read about another compound, sodium compound, which is sodium hydrogen carbonate, which is simply baking soda, which is used in our house. Sodium hydrogen carbonate is known as baking soda because it decomposes on heating to generate bubbles of carbon dioxide. It is used in cakes and pastries to make them fluffy. As the carbon dioxide gas is released, it forms bubbles and the cake becomes fluffy. Sodium hydrogen carbonate is made by saturating a solution of sodium carbonate with carbon dioxide. The white crystalline powder of sodium hydrogen carbonate, being less soluble, gets separated out. Now, sodium hydrogen carbonate is a mild antiseptic for skin infection. It is used in fire extinguishers. Now, what is the biological importance of sodium and potassium? A typical 70 kg man contains about 90 gram of sodium and 170 gram of potassium, compared with only 5 gram of iron and 0.06 gram of copper. Sodium ions are found primarily on outside of cells, being located in blood plasma and the interstitial fluid which surrounds the cell. These ions participate in the transmission of nerve signals, in regulating the flow of water across cell membrane, and in the transportation of sugars and amino acid into cells. Sodium and potassium, although so similar chemically, differs quantitatively in their ability to penetrate cell membranes, in their transport mechanism, and in their efficiency to activate enzyme. Thus, potassium ions are most abundant cations within cell fluids, where they activate many enzymes, participate in the oxidation of glucose to produce ATP, and with sodium, and responsible for transmission of nerve signals. There is a very considerable variation in the concentration of sodium and potassium ions. Potassium ions found on the opposite sides of cell membrane. As a typical example, in blood plasma, sodium is present to an extent of 143 millimoles per liter, whereas in potassium levels is only 5 millimole per liter. Within the red blood cell, these concentrations change to 10 millimole per liter for sodium positive ion and 105 millimole per liter for potassium positive ion. These ionic gradients demonstrate that discriminatory mechanism called a sodium-potassium pump operates across the cell membrane, which consumes more than 1/3 of ATP used by resting animal and about 15 kg per 24 hour in a resting human.